Hi, everyone. Welcome to another Talk Math with your friends. It's my pleasure today to introduce Dr. Courtney Gibbons of Hamilton College. She is going to be telling us about her real friends, Betti Numbers, not us, apparently. But before that, she did want us to ask if anyone watching this talk is at all familiar with WordPress. She would like some assistance with fixing her WordPress installation so she can bring back her cartoon brown Sharpie. I think we see some for doodles right here.
Thank you for that introduction. And if you are willing to, log into my whatever DreamHost account and fix brown Sharpie, that would be awesome, because I have aged out of that kind of thing. It turns out I've hit that magical age where I can no longer manage technology very well. So thank you all for coming today. I'm really excited to be here. We're going to talk about lots of stuff, like how cats eat you after you die, but also Betti numbers. So let me get my iPad awake again. So I thought I'd start by just, since we're chatting, asking where you are. And I'll start. I'm in Clinton, New York, which is in what has historically been the home of the Oneida people. And I'm not a native. I'm not a native of New York, but I'm also not indigenous to this country. And so it's really interesting if you're to figure out, who has been displaced by all of us who are here, or if you're indigenous to the U.S., where are other people who are indigenous to the U.S.? Where have they come from? So where are you? Where is everybody? You can just unmute and shout out.
Try Dublin, Ireland.
Wow. What time is it there?
8:35 p.m.
Oh man, I hope you have a beer or something.
Now I got water. I tried this a few weeks ago with whiskey and it didn't work too well.
Okay.
You know where I am, Youngstown, Ohio.
Awesome.
But I saw some Columbus, Ohio people.
Excellent. And I see some folks in the chat from all sorts of places: Michigan, Florida, New Jersey, Boulder, Colorado. Oh man, I went to undergrad at Colorado College in Colorado Springs, and I miss real mountains. They say we have the Adirondacks here, but they're a little short.
Peoria, Illinois, Bradley.
Awesome. Oh, and I see one of my linear algebra students is here. So, man, he's just volunteering. He's just volunteering for extra punishment today.
Hey, wait, who's here from Bradley?
Me, Ollie.
Oh, I'm at Rose-Hulman.
Oh, cool.
Oh, that's exciting. Look at all these connections we have among friends. These are relations that we're finding here, which is key to the idea of Betti numbers. Just file that away for later. I thought we might have a brief pep talk before we get into any math, because it's 2020. I don't know if you have noticed that it's 2020, but I have been noticing like a global 2020 awfulness that's happening for all of us, and then also some local 2020 awfulness that's happening for each of us. You're all having our own experience of 2020. So I wanted to give a little pep talk. And as I was thinking about the pep talk, I realized it starts out in kind of a low place, but it gets better. So today is like 2 days away from the 20th anniversary of an event that completely changed my life. And it's not one of those like good life-changing events. It's one of those really like bad life-changing events. And as a result of this thing, I dropped out of college in my first semester. I moved back home with my parents, where I was very emotionally unhappy because I'd always been a pretty good student. And now here I am, a college dropout. I was mentally not very happy because I didn't have anything cool to think about except, like stewing on, oh my gosh, now I'm a college dropout. Physically, I was not in great shape because I was thinking about, like, how do I manage to like disappear? Because I'm very embarrassed now that I've gone from being like a pretty good student to a college dropout. And I thought that was pretty much the worst. Like that was the worst my life could possibly be. Now it's 2020 and I've revised that, right? Like it can get a lot worse. But aside from all of the actual real badness that happened, one of the shining things that came out of all of this was I eventually went back to school, and then I kept going, and now I guess I still sort of am in school because I teach at a place a lot like the place that I finished my undergrad. But math is this thing that has been one of my friends for a while. Math was the reason I went back to college, because I was kind of annoyed that I had hit some problems in this calculus book that I still had that I couldn't do. And I was like, I really want to figure out how to do these stupid problems. So I went back to school to take some calculus to figure out how to do these problems. After I finished my first year, I transferred. So that's 3 undergraduate institutions, if you're keeping track. I transferred to Colorado College, where it was awesome. You took one class at a time. My first math class there, Calc 3, I was completely hooked and like just slid into a math major and ditched all my plans. And the people that I've met through mathematics are just the best people. And so even though it's 2020, and even though probably none of us are living the life that we expected, either starting in 2020 or starting before, I think we all probably find some solace in mathematics as something that we do to keep ourselves entertained and happy, but also as a way to
Why this is not on?
Our community of people. So that's a pep talk. Yes, it's a long pep talk, but I'm excited to be here because one of the silver linings of my 2020 has been the Talk Math with Your Friends series, which reminds me of these wonderful people that I'm in community with all the time. So I hope that you are also finding something in your 2020 that's not completely terrible. And I want to thank the organizers of Talk Math with Your Friends, because it's really been a bright spot for me. Okay, on to the good stuff, on to the math, if you're not here for the emotions. As I was doodling these little hearts on my slide, I realized, this heart kind of over time morphs into a beta. And beta is the symbol for Betti numbers. So we're going to talk about some Betti numbers, and I promise we're going to get there. But I wanted this to be a gentle ease in. So I want to start with a question. Let's start with a question. What is 2? And when I say that, I mean, what kind of question is a good question if you want to get the answer 2? Any thoughts?
What's better, 1 or 2 Courtneys?
Okay. How many Courtneys is best?
This guy shouldn't be unmuted.
I guess that's probably not an apostrophe there. What else? I hear a cat purring. I'm not sure how to interpret that.
Right. It's always right.
What is 1?
What is,
How many cats should we have?
how many cats should we have?
I think 2 is about like perceiving objects, but being able to perceive like multiple ones and separate the things we experience in the world. So what's the smallest interesting amount of stuff?
I really like that question. What's the smallest interesting amount of stuff? Anything else come into mind?
There's a lot of stuff in the chat,
Oh, awesome.
starting with what is the number after 1?
That's a good question.
What prime am I scared of?
2, the oddest prime. That's a joke. Feel free to laugh at that.
It is good.
How many orientations of a thing? Yeah, these are all great questions. And the one that I want to zero in on today, Alicia hit it right off. How many Courtneys is best? But I really want to think about the question, how many? How many? And actually, I really also like, what's the smallest interesting amount of stuff? That's actually going to come in too. How many cats should we have? I think infinity is the correct answer for that one. But That's not very practical. So 2 is pretty good. Okay, so when people talk about Betti numbers, and I scoped out the internet a little bit to see like what kind of videos are out there about Betti numbers, and this idea keeps coming up of like how many holes does something have, and I'm curious to know what your answer to the question, to this question is. How many holes does a straw have? So here's a straw. I see 2, 1, 1, 2, 1, 1, 1.5. Okay. Geometrically 2, topologically 1, 1, 0. Hole relative to what, a sphere or a disk? 1, 0. These are, what is a hole? What is a hole? Excellent. Thank you. What is a hole? It's like such an imprecise idea. What is a hole? And I know some of the Hoagie Homies crew is here. This is like the math version of, is it a sandwich, right? We want to know like, what is your definition of a hole? Let's make it precise so that we can classify whether things are holes or not. So I want to start by talking about a torus. And if you're not used to the word torus, think of it as a hollow donut. And if I ask you how many holes a torus has, you might think of something called genus. And the genus of the torus is 1. It's got 1 hole, and that's, you know, like the hole in the middle. But I want to talk about something a little bit other, like different than holes. I don't really
You're
like.
talking about a solid torus or a 2-dimensional?
I'm talking about a torus with no inside. So just the surface of a torus. Okay, so I want to think about something other than genus. And what I want to think about is this idea of torsion. So torsion probably has a fancy definition in a dictionary, but the way that I think about torsion is it's like something that twists back on itself, right? And so I'm going to unravel this torus, and I want to talk with you about torsion a little bit to lead into Betti numbers. So when I say I'm going to unravel this torus, what I mean is I'm going to take my torus apart by cutting it like here. So I'm making a pink cut, and then I'm going to cut it like here and make that blue cut. And when I do that, what I've done is I've basically unraveled this thing. And if you want to see if you believe that that's true, imagine folding the pink sides together and you get a straw, which has some unknown number of holes, as we discovered in the chat. And if you then bend it together, so the 2 like ends of the straw are connected, you get a torus again. And the way that I think about torsion is I want to draw a circle on the torus. And if I draw this circle on the torus, my claim is that this isn't a super interesting circle, because I'm pretty sure that I can like squeeze it down, and I'm not going to like hit any interesting feature of the torus that prevents me from squeezing it down. So I can squeeze that circle down to a point. Guys, anybody have questions about that idea? I'm talking about this like contraction to a little point. I'm not doing anything super interesting.
You haven't cut through the tor or through the flat surface. You've literally just drawn a circle on top of the flat surface.
Exactly. So it's like I'm drawing that circle just on the surface. I'm giving my torus a tattoo, and it's not a super interesting tattoo. I mean, I could also draw this circle, but that turns out not to be super interesting either, because I can just drag it over to that circle. I can just sort of slide it around the torus till that's like that circle. I could just slide it over there, and then I can contract it down. I think there are some interesting circles that we could draw on this thing that are a little more funky. Does anyone want to, I'm going to ask for math by pantomime here, and I'm going to make sure I can see all of you. Any ideas of how we could draw a circle? Okay, I see BK, who's doing some kind of disco. I
like
see
around the other hole.
around, yeah, these are, oh man, you're beautiful. This is a beautiful group of mathematical dancers. So I think BK is saying, oops, I didn't mean to erase that. I think BK is saying, draw this circle that kind of goes around like that. So if I glue this thing together, now I'm sort of trapped around one of the holes of this thing. I saw somebody saying, draw that circle, which is like now going around the other way, sort of like parallel to the pink circle. I think TJ was saying something like, draw a circle like this, but then that comes over here, and then that comes over here, and then that, and that's a really complicated circle because we have to keep tracking it and seeing where it goes. So that's a super wound around the torus circle. Here's a question for you. Can I drag the purple circle, the one that's going vertically, in case my colors are hard for you to see, can I drag that circle around and turn it into the green circle? I see some head shakes.
Yeah, I think I see what you're on.
So like if I try to wiggle this purple line a little bit, let's see what happens. So I'm a fan of math by experimentation. So if I wiggle it a little bit like that, to try to like start moving it toward the green circle, well, what happened is I came up here and I kind of like just made my circle like a little bit more complicated. And then I got caught over here. And the more I try to get it to be the green circle, the more I'm going to fail at getting it to be the green circle. So BK's suggestion earlier was like, what, like, you know, the most interesting amount of stuff, the first most interesting amount of stuff to perceive is 2. I see that there are like 2 fundamentally different circles on my torus. There's the one that's parallel to my pink cut that I can slide around the torus, and the one that's parallel to my blue cut that I can kind of slide around the torus. And that is actually, we drew a one-dimensional, you know, we drew these like one-dimensional curves on the torus. And that is what we're thinking about when we think about a Betti number. So the Betti numbers are going to keep track of like, how are you creating interesting relations with different dimensional objects. And I'm not a topologist, so I'm probably going to butcher the first Betti number is the only one I really get. I do Betti numbers in algebra, which we're going to talk about soon. But if I look at beta 1 of my torus, there are 2 interesting ways to draw curves on this thing. 2 fundamentally interesting ways to draw curves on this thing. So cool. We've got like the one-dimensional kind of stuff going on, the curves we can draw. If I think about like how many sort of finite pieces of 2-dimensional space do I need to build my torus, that's going to be my second Betti number. And the fact that I've drawn one rectangle here might be suggestive. That tells me I'm going to need one thing here. You could sort of think about it as like how many regions of space does this thing trap? It traps one region of space. I haven't done anything with 3-dimensional space because that scares me. I'm going to be honest. I thought I was going to be a geometric group theorist, and then I started to see all these weird pictures and stuff, and I said, I better stick to polynomials, which I understand and can think about. So beta 3 of my torus is going to be 0, and so on. My nth Betti number and higher for anything greater than 3 is going to be 0. The weird one is beta 0. So this is the way that I think about this is I can put a point on this thing in one way, and then anywhere I draw a point, I can drag it around and I get the same point back. If I had drawn 2 distinct tori, there would be 2 ways to put a point on it. So then I would have, it's essentially like counting your number of connected components. So this is 1. And of course, I don't have negative dimensional stuff. So if n is less than or equal to -1, we're gonna, I don't know if we say it's 0 or we give it a question mark because I haven't actually checked with a topologist. Any topologists want to chime in? Would you say this is a nonsensical idea, or would you call it 0?
Justin says palindrome.
It is a palindrome. So if we want it to stay palindrome, I'd probably call those 0 as well. So these Betti numbers are named after Enrico Betti. And he didn't call them Betti numbers after himself. Poincare is actually the one who named Betti numbers for Enrico Betti. And Poincare himself, I don't know if you've seen Poincare series, but we could write these Betti numbers as a series where I say, all right, I'm going to have a dummy variable t. And I'm going to say the t to the 0 coefficient is going to be the 0th Betti number. So I'm going to get a 1. And the t to the 1 coefficient is going to be the first Betti number. So I'm going to get a 2. And the t to the second coefficient is going to be the second Betti number, b2. So I'm going to get a 1. And everything else is 0. So the Poincare series for my torus is a generating function, if you want to think of it that way, or it's basically a way of seeing all the Betti numbers as a series. One of the reasons we might want to do this is because maybe in algebra, we might run into some infinite series. And gosh, I wish there were a subject that talked at length about infinite series and what happens with them. But I don't know. I can't think of one, probably because I'm not teaching Calc 2 right now. But we've got a lot of tools for dealing with series. So if we can imagine Betti numbers as series, we can ask really good questions about them. But as someone who's not a topologist, I want to move on to algebra so that I can write down something that actually does have an infinite series. So let me stop here though. Any questions about this stuff so far?
I haven't thought about this, or if I have, it's been 15 years. Is there something like a topological product that corresponds to like a product of the two polynomials?
Oh, gosh. I don't know. That would be super awesome. That would maybe come from a mapping cone or a mapping cylinder. Maybe that's how I would try to do it in algebra, but I'm not sure.
Cool.
So, okay, so you don't have any questions. I have a question for you. I've made this critter. It looks a little bit like Stitch from Lilo and Stitch, I think. And I'd like to know if you can calculate the Betti numbers of this thing. So I will be quiet and I will let you think about this. Would you like to go into breakout rooms and work with a group?
Are those things touching?
They
Or is
are.
it-
They are.
they're-
These are.
Okay.
There are little points where
Right.
these are connected, and this other thing, this like other guy is floating around next to it. Anybody think they know beta 0? All right, yeah, you can just give me a hand signal. Yes, peace, friends. It's 2. Right, I've got 2 connected components. If I drop a point on my little, I don't know, bunny shaped thing, I can drag it around to anywhere else on the bunny. But if I drag one over here, so I've got 2 different interesting ways I could put a point on this thing. How about beta 1? How many interesting circles are there?
We have guesses of 2 and 4.
All right, guesses of 2 and 4. I think I see one interesting circle here, and its friend, another interesting circle over here. And I think those are stuck on that torus. I don't think that I can move them around. So for those of you who saw 4, what were the other 2 that you saw?
On the other torus.
On the other torus. Cool. So like we've got these buddies over here. And then on the spheres, oh, let's see.
I could take one of the pink ones and it would end up, I could go from the left pink to the right pink, couldn't we?
Let's see. So
I
if
could
you
do it- I
try,
could expand that, I could expand the cut on the left, go down around the base of the 2
so
spheres.
you're saying like bring this guy down here,
Back up the other side.
back up the other side over
Into
here.
this thing up here.
But I'm
all
still,
the way back across the top. Yeah,
yeah, maybe down again
yeah. And back up, yeah.
and back up.
So like freely generated on those four rather than independently generated on those four.
Yeah. So I, not being a topologist, think when I worked this out, I got a 4, but I'm giving this a 4-star because I'm not actually sure, because I'm not a very good topologist. So how about beta 2? How many regions of space have we trapped? That one I think is the easier one.
Most of our guesses are 5.
Most of our guesses are 5. Yeah, I see 1, 2, 3, 4, 5. I think if I tried to put a circle on the sphere, I could contract that down to a point. So there aren't any interesting circles on my spheres. And then there's sort of if we take these two tori and put them together at a point, essentially, right, we could sort of reduce this down. That's always a good strategy, mathematically, reduce it down to a simpler problem. If we had 2 tori joined like that, how many interesting circles do we have? I think the answer is 4, but I've got at least, okay, Ollie's with me. Ollie says I'm right. And so I'm gonna take that as good.
I think
Okay.
fundamental group is going to be the free product of the fundamental groups of the 2 tori, I think. It's been a while.
That's what I remember from working out an exercise a lot like this, but my topological intuition has degraded over time. Well, let me tell you the secret here is that I drew pictures to get you interested in Betti numbers, but I actually don't care about the pictures very much. I want to think about this from an algebra point of view. I have this slide here. What is 2 plus 2? Which is a little bit of a joke because you may, if you're on Twitter a lot, you may remember the great Twitter 2 plus 2 moment of the summer, which led to some really excellent conversations about the nature of mathematics and where it comes from and who gets to be a math authority and stuff like that. I want to modify the question a little bit and ask, what is 2 plus 12? And I want to have a much shallower conversation because what I want to do is clock arithmetic, right? If I take 2 o'clock and I add it to 12 o'clock, what do I get?
2 o'clock.
2 o'clock, awesome. And if I take 2 o'clock and add it to 11 o'clock, what do I get?
1 o'clock.
1 o'clock. Okay, you're all way better at arithmetic than I am. So that's good news. This is going to make this part of the talk that much better. But I have a notation for this little clock arithmetic set. I'm going to call it Z12. We're really interested in things like the remainders after you divide by 12. If I work 3 5-hour shifts starting now, which for me is 4 o'clock, what time will it be when I finish?
What
7
time is
o'clock.
it for you? 7.
It's 4 o'clock for me. I'm going to work 3
Más
5-hour
3, yeah.
shifts. And it's then going to become 7 o'clock. And so Jesse, you did that. How'd you figure that out, Jesse?
I knew 12 would get me to another 4. So
Awesome.
I decomposed 15.
Awesome. So if I do 3 times 5, I get 15, but then I'm going to reduce that mod 12 and get 3. So we also, we can add mod 12 and we can multiply mod 12. And we all kind of have some intuitive sense of what we're doing. So this is a nice little algebraic structure called a ring. And if that word means nothing to you, don't worry about it, but it's one of the best algebraic structures out there. Means it's got addition and multiplication and they behave really nicely. Oh, I see some heart reactions, which just warms my heart. Thank you for those. So, all right, so I've got Z12 and I want to make a function that goes from Z12 to C12. And I know I'm drawing my function arrow the wrong way, but it's my talk. So you're going to have to let me have my way. And you're going to see why this makes sense later on because you'll see why it makes sense later on. I want to multiply by 4 and I want to see what happens. So in my set of things mod 12, I'm going to call 12 0 because it's really the additive identity. If I add 12 to something, I don't change it. So it's the 0 in here. And also 12 divided by 12 has a remainder of 0. So I've got 12 things. And if I know where each of these things goes, I'm going to have a complete and total function definition. So if I take 0 times 4, give me a pantomime. Oh, you're so good at this. You get a 0. If I do 1 times 4, get a 4. 2 times 4, get 8. 3 times 4, another 0. 4 times 4, 4. Oh, this is like the Macarena, but for math people. 5 times 4, I'm going to get 8 again. Okay, and you guys have caught on to the pattern here, I think.
I'm gonna have to mute myself. That's too funny.
Please don't mute yourself if you're laughing at my jokes. Please.
No, Brian was doing the Macarena.
Oh, okay. Well, all right. If you're laughing at someone other than me, then you should mute yourself, because I have a very fragile ego and I want to be the only funny one in this Zoom call right now. No, that's okay. Excellent. So we're doing the figurative or literal Macarena here. And we see that we end up getting, 3 possible things here. Okay, back to this idea of torsion. In our torus, we got some torsion when we drew a line and it sort of circled back on itself in an interesting way. In algebra, I think of torsion as a surprising way to get 0, right? Like 0 is sort of this interesting fundamental object. And I want to, like, if I multiply by 0 and get 0, I'm not surprised. I'm like, great, like, duh, any sensible operation that should happen. But if I multiply by 4 and get 0, I'm like, wait, that's kind of interesting. Like, something cool is going on here. And I might be interested in, then, if I'm curious about how do I get 0, what is the kernel of multiplication by 4? Which is just a fancy way of saying, like, what are the things that I multiply by 4 and get 0? And in this case, what do 0, 3, 6, and 9 have in common?
That you can divide chocolates with 3 people with that many chocolates.
Yes, that's good. I like that example. If we have this many chocolates, we can divide it evenly among 3 people, and we're not going to start a fight. But if we have 4 chocolates and we try to divide it among 3 people, I'm just going to eat all 4, and then there's no fights. But okay, so the kernel here is the multiples of 3. All right, multiples of 3. I want to build a function from Z12 to Z12 where what I get out of that function are the multiples of 3. Now, when I did this with multiplication by 4, if I look at what happened, sorry, that notification was for a committee meeting that I'm not going to because I'm here instead. Yes, this is way better. I'd much rather be talking math with my friends. If I look at the image of multiplication by 4, I got things that look like 0, 4, 8, 0, 4, 8, 0, 4, 8, 0, 4, 8. Those were the multiples of 4. So if I want to build a function whose image is the multiples of 3, what function is that going to be?
Times 3?
Times 3, exactly. You guys are so good at algebra.
Mm-hmm.
So I've got the times 3 function. And that, here I've built a map where the image of this map is the kernel of the one that comes after it in terms of function composition. Now, if you're really interested in syzygies, which is what we're building here, also excellent hangman word, S-Y-Z-Y-G-Y. I have a link to it. I thought it'd be a good idea to try to explain syzygies in 5 minutes at an event. So you can go learn all about syzygies, become an expert in 5 minutes. But what we're doing is we're matching up the image and the kernel of these maps. And I want to count how many copies of Z12 do I need to do as I'm doing this. And somehow I'm going to be this object here, if I stop here, then what I end up getting is Z12, and I think of modding out by the multiples of 4 as a ring. If you are happy thinking about rings, you can show that's isomorphic to Z3 as a ring. If that doesn't mean much to you, that's okay. But this might be like the algebra version of my torus, right? Like I might be interested in this thing and I'm asking like, how many interesting relations does it have? And then what are the relations among those relations? And then what are the relations among the relations among those relations, and so on. And if I keep doing this, well, the kernel of multiplication by 3, if I want to get things that are divisible by 12, is going to be multiples of 4. And then the kernel of multiples of 4, we already worked out, that's multiples of 3. What we just built was an infinite free resolution of this module, and if you want the jargon, but we just built this like long infinite chain of maps, and we can count, and we can see there's, if this is our beta 0, there's one copy of it here. There's one copy of my ring in the first step. There's one copy of my ring in the second step, and so on. And so my Betti numbers are all 1, starting with beta 0. And if I want to write that as a Poincare series, I get 1 times t to the 0 plus 1 times t plus 1 times t squared plus blah, 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 1 times all of those things, which kind of reminds me of this series. And if you were in a calculus class and I said, what does this thing converge to on its radius of convergence? You would answer.
Radius of convergence 1 or less, and then the 1 over the 1 minus the t.
Yes. Gold star for Alicia. And because I'm an algebraist, I don't care about radius of convergence. I mean, I sort of do. Sorry, Alicia looked horrified. I sort of do, but this t, I'm not going to really plug anything into it probably. I'm just sort of saying like, what does the growth of this thing look like? And it looks like a geometric series. It's like I could expand it out that way. There are some things like if you're interested in asymptotics of Betti numbers, like what do these things look like? You could define things like curvature of the Poincare series or curvature of the Betti numbers for these things. And it's going to be 1 over the radius of convergence. So the curvature of this thing is not very interesting. The curvature of this thing is going to be 1. But what I really like to look at are Betti numbers that are infinite. And I like to think about sort of like, what are their asymptotic properties? And so curvature and things like that from calculus, where we deal with these series and how do we mess around with these series, turn out to be really useful.
I have a question.
Yeah.
So, I mean, you picked the 4 and that sort of determined everything else in your long, whatever, exact sequence. So are the Betti numbers about the sequence? They're not about the ring because you could have chosen something else. What are they about?
They're telling me about they're telling me about this object. So secretly, I didn't tell you this up front, but I was interested in this object. I want to know like how many generators does this object have? And it has 1. If I think about like, how do I get Z3? It has 1, like, or this thing that we got, let's say it has the generator 4, and then I can add 4 to itself. And then I can, anyway, if we think about it as a module, we can multiply it by anything from Z12, and what we end up getting is 0 through 0, 4, and 8, right? So it's got 1 generator. And then I'm like, okay, so does that generator have any relations? Is there anybody in Z3 that has some interesting interaction with 4? It turns out 3 has an interesting interaction with 4. So there's a relation with the relation. And then I ask, okay, does 3 have any interesting partners in Z12? Turns out 4 works that way as well. So I'm really sort of asking like about generators along the way, like how many generators do I need? And once I figure out like what those generators are, I'm thinking like, okay, let's look at that kernel. How many interesting relations are there? And that gets at torsion because it turns out that these numbers, beta n for my thing that's called a module over here, if you are happy with functors like tor, and if you're not, just, think about kittens for a minute. But if you're happy with things like tor, we're looking at like the nth tor over r of our module with something like a residue field, like a base field. And
you have questions in the chat that I cannot even understand the questions, but I'm going to read them. So this thing has one generator, but we say 2 is interesting. Can you do the same sort of thing for stuff with 2 generators?
I'm so excited that you asked because I really want to
Oh,
do.
I didn't.
Yeah.
Make
Well,
it clear.
Meredith, I'm so excited that you asked because I want to do the same thing with something with 2 generators. And while I'm doing this, let me show you which thing I want to do this with. This ring that I'm going to play with is sometimes called the Emmy ring for Emmy Noether. And it's called this because it's a ring with a lot of interesting properties. If you're into commutative algebra, it's a nice example of a ring that's not Cohen-Macaulay. Its depth and its dimension are different. If that's a bunch of jargon, don't worry about it. We're going to look at this ring. So it's a ring of polynomials with variables x and y, but we've got some relations. We're imposing some relations on these things. X squared is 0 and xy is also 0. And so this green polynomial that I wrote, there are some terms that don't actually need to be there. Which terms can I cross out? The first one, it's got an xy, so that's a 0.
The third one has an x squared.
Yep. And that's it. So essentially I'm saying I can reduce these polynomials down to their remainders after I divide by x squared and xy. So this is a ring, and I want to build this thing called a module, which is like a vector space, but the scalars come from the ring. And I think I just gave at least one student in my linear algebra class a nightmare because we just started vector spaces, but it's okay. Vector spaces are great. So I want to take my ring and I want to mod out even further by x and y. Oh, and k here is my stand-in for a field. You can use your favorite field. Let's call it the complex numbers. And I'm going to think about this module, which is essentially then just my field because I'm setting my variables all equal to 0. Let's see what happens if we try to find the Betti numbers of this M. So here's my M. Now M is a quotient of this ring, and so it has one generator. I take R and I take R's generator, which is 1. I can multiply 1 by any polynomial and get any polynomial in here. So it's got one generator, and I'm just going to take it and send it merrily on its way to the constant polynomial 1 when I mod out by x and y. And if you like, I'll put a bar on it so that we know we are in a further quotient. And the way that I get M to look like that is I take 2 copies of my ring and I'm going to do matrix multiplication. I'm going to multiply by x squared and xy, the generators of the thing that I killed off. And this is why I draw my arrows backwards, because we're about to do matrix multiplication and it doesn't work if you draw your arrows in the other direction. So anyway, you've all been drawing your arrows the wrong way the whole time. And I'm sorry that I had to be the one to break it to you. So, okay, so I've got this thing and now I want to look at the kernel of this thing. And so the kernel is going to be my column vectors, f of xy and g of xy, where when I multiply by x squared xy, oh, sorry, you guys didn't stop me. I'm not resolving R, I'm resolving M. That's just an x and a y. I was like, this is about to get hard. It wasn't supposed to be hard. This is supposed to be fun and easy. Okay, so I multiply by x and y, and I get 0 in my ring. My cat, I don't know if you can hear her, but she's so excited right now. She's like, oh, this is the good stuff. This is why we do math. So I've got this thing. So this says xf plus gy or yg equals 0. And I want to figure out sort of the simplest way to pick some f's and g's to get 0 in my ring. Remember, 0 in my ring is weird. It could be 0, or it could be a multiple of x squared, or it could be a multiple of xy, or it could be a sum of multiples of x squared and 0 and xy. So any thoughts on something nice that's in the kernel?
Who points out any multiple of x?
Oh, yes, I got it. Oh my God. Sorry. This was like me too excited because I was thinking x, and then somebody said it, and it was.
Exactly. Yeah. So like if I make fx, then this thing, and you know, g 0, then I get x squared. So that's in my kernel. But I can also make,
XX.
yeah, so like XX is a combination of X0 and 0X. So those are sort of like two, like think of these as the two different circles on our torus, right? There's like a circle going in one direction, a circle going in the other direction. And I think there's one more thing.
Can we put Y in F?
Oh, yeah.
Yeah, if we do that, then we've captured all the interesting ways of making 0 with these two polynomials. What that tells me is if I'm going to make this the image of some map, it's going to be a matrix, and it's going to be a 2x3 matrix. And the first column is going to be x0, and the second column is going to be 0x, and the third column is going to be y0. And now I have 3 copies of R. So as I'm going along, I'm calculating my Betti numbers. I've got beta 0 is 1, beta 1 is 2, beta 2 is 3. If I tell you that beta 3 is 5, and it is, what do you hope beta 4 is going to be?
8.
8.
8. And what do you hope that beta 5 is going to be?
11. 13. 13.
Yes. Yes. So this is it's okay. It's good. This is great. Alicia, I'm so happy that you're enjoying this because you seem so scared of Betti numbers at first.
Well, it's because then you put like the little diagrams. It's exactly when I decided, no, not doing pure math. No, these things are weird. But if you had taught me, I might have been a pure mathematician.
So it turns out that the Emmy ring, if you take the field, the residue field that you get, or the constants that you get, you end up getting that the Betti numbers, if you write them out as a sequence, gives you the Fibonacci sequence. I guess we missed the first one, but we could probably cook up a ring like this. And so we've got this cool example of a ring that has the Fibonacci sequence as the Betti numbers of some module. So what questions does this make you want to ask now?
Is there like a thing, like one of those thingies for any sequence I want?
Yeah, can you get any sequence that you like as the sequence of Betti numbers? So what sequences can we get as Betti numbers?
Kim asks, can we get a sum of 2 sequences in some meaningful combination of the rings?
Sum of 2 sequences.
And
from good algebra, I'll call that.
And I was thinking, to what extent do the Betti numbers determine the isomorphism class of your ring? Like, can 2 rings have the same sequence but be very different?
That's a really good question. What is extent do Betti numbers determine the isomorphism class? I'll just call it the ring. We'll say if 2 rings are isomorphic, we'll just call them the same.
Mm-hmm.
So these are all really, really good questions about Betti numbers. The first question, there's a conjecture out there that says we can get sequences as long as they're eventually non-decreasing. So a sequence that ends with a bunch of zeros because it's finite, that's fine. That's eventually non-decreasing. 0 is eventually non-decreasing. Fibonacci sequence, that's always non-decreasing. And so far, we don't have examples for commutative rings, either in the local case, which is where most people do this, or in the standard graded case, where we can find something that's not eventually non-decreasing. So this is a pretty cool conjecture. And one of my advisors, I think, is the one who stated it. So that's Avramov. If we take the sum of 2 sequences, like, can we get that sum from like some good algebraic process of putting 2 rings together? And there's some really cool stuff that we've stolen from topology, like mapping cones. I remember the first time I saw a mapping cone in topology, I was hooked. I was like, I want to build this machine and I want to see what I get from it. It's so cool. But then I'm a bad topologist. So once I learned I could do it with polynomials, I was like, yes, that's where I want to do this thing. So there's all sorts of like constructions that you can use to try to put stuff together. And that gives you ways of like adding sequences together and coming up with these sequences.
It seems like the direct product of the two rings.
I think
would at
that
least-
probably should work.
Okay.
Yeah, the direct product, you could add up some sequences and take your modules that have those sequences, take their direct product, and now you've added no new relations among them between the two rings, and you also haven't killed off any relations. There's some things you can do like the tensor product instead of the direct product, where now you are adding like new relations, and that's all sorts of weird and fun. And so like, when is the tensor product nice is a good question. To what extent do Betti numbers determine the ring? I love this question because this is one of my favorite questions to ask about these things. And it leads to this area that I work in called Boyce-Soderberg theory. And I'll tell you, I was just a naive young undergraduate when Boyce-Soderberg theory was happening. This was around 2006. And then as a graduate student, these proofs of some of these conjectures that were in this initial paper were coming out, and I got hooked. And so this is part of what my dissertation work was on. But it's kind of like, if I take this sequence of Betti numbers, so I'm going to draw a picture. And this is kind of, we didn't talk about what the shifts mean when you move stuff down, but there's a way of interpreting this as Betti numbers where you pay attention to the degrees of polynomials involved. Like if I'm multiplying by degree 2, it's going to be in a different place than if I'm multiplying by degree 3. And it turns out that there's not a module out there in a nice sense that's got this good Betti table, but there is a module that has this one, which is just 2 times the other one. So if I think about these Betti tables or Betti numbers living on rays in some nice vector space, maybe I can't get that one, but I can get 2 times it. And maybe, over here, I can get that one, but not the ones before it. And maybe I can take these two Betti things and do a direct sum or a direct product and get something that's sort of like on the little face between these two things. Like I get something in here. So you can start asking about global properties of Betti numbers over one big ring, and they lie on this cone. And now you can start doing convex geometry. And it's almost like you ended up being a topologist after all, which is really kind of exciting. And anyway, this is really fun. Boyce-Soderberg theory is about rational multiples of Betti diagrams. Betti diagrams are integers, but what happens when you take rational multiples of them? Now you've got a whole nother toolkit that you can play with, which is pretty exciting.
Two other questions. One,
yeah.
Meredith wondered if, so not an algebraic geometer, but do we know something about the sequences and varieties that go with the ring? So maybe like a special subfamily of rings, whether they have nice Betti numbers. And then Joshua asked, is there a combinatorial explanation?
Is there a combinatorial explanation? Probably, but I don't know it. In some cases, there probably is. There are some cases where if you work in I think the example I'm thinking of is a paper from the 80s where you have this interesting combinatorial way of walking around monomials to figure out what the relations are, but it's in a non-commutative ring, which is sort of cool. So it's the Anik resolution. I want to say 80 or 81. So that has this nice combinatorial way of, and it's sort of like you're trying to solve the word problem because you're looking for these relations, and that's actually really hard. But it takes a combinatorial approach, which is cool. And then you can do it in the commutative case as well. In terms of the geometry, there is a way that you can sort of link the Betti table to the dual space, which is cohomology of coherent sheaves, but all of those words give me nightmares. So I'll say that there are some things out there, but I am very much not a geometer, and I leave that to you to explore and tell me about someday on Talk Math with your friends, Meredith.
Oh, no worries. I was actually asking the crowd as a whole because I know effectively nothing about this. So I was like, she said she's not a topologist. I don't know if I can. Anyway.
I will skip to my last slide. It's been really fun to talk to all of you, and I want to make sure that we don't run over in case any of you have committee meetings to go to. But
no, let's run over and let's not go.
okay, that sounds good. I would love to talk math with you more. Here are a bunch of ways to get in touch with me. And this has been really fun. Thanks for hanging out.
Courtney, this is awesome. Everybody enjoying it.
We have about 3 minutes left, so let's do our announcements, and then we have at least one question from Justin. Our main announcement is you should come back next week. Alicia is talking. Alicia, do you want to tell us like 30-second or less preview?
Sure. I am going to just, as I do all the time, explore why I teach the way that I teach by figuring out what I did before in my life. So that's a terrible preview.
Excellent. Thank you. Great. And yeah, so Justin, you want to ask your question out loud?
Oh, sure. Could you just run it by us again? What is the algebraic object or data along with it that has Betti numbers? Is it a ring or a module or maps between them?
That's a good question. It's the module is the thing that has the Betti numbers. And the way that you count them is you take direct sums of your ring, which gives you a free module. And so you're looking at the dimension of the free module that you need to like capture the number of relations that you have at that step.
Cool.
Yeah.
All right. Thanks for the talk.
Yeah. I think I caught most of the rest of the questions. Anyone else have something they want to ask?
And I'll say there are a few other experts on Betti numbers in here. I see Spencer, who knows some stuff about Betti numbers. We worked on a project together a while ago. I'm sure Moira knows some stuff about Betti numbers. And I'm sure Drew, yeah, go ahead.
Are there other like famous sequences that we know a module that has those Betti numbers? Somebody mentioned Lucan numbers.
Yeah, so I think there's a paper by Gwyn Wielden that you can find where she talks about like if you have cool sequences, how to build them. I know that I have an example of something that has the Lucan numbers and then sort of like the generalized versions of those you can build. It's like the ring is, you build a Kazul algebra, it's a short Gorenstein, anyway, jargon. Yeah, you can build these things with some interesting sequences.
Cool.
Sweet. Well, that's about our time. We can hang out for a little while, but let's clap to end our video.